Okay, we're going to finish up actually the chapter today. We're going to look at some practice problems using Gibbs free energy. Okay, so if we have this reaction, we have carbon monoxide plus water. We end up with carbon dioxide and hydrogen. And again, they're all in the gas phase, and it's important that you put that little number. Okay, if the delta H, if it's already determined as negative 41.2, and the delta S, the entropy, is negative 135, again, joules, so I'm going to have to fix that. And the temperature occurs at 298 Kelvin. And again, when you do Gibbs, because these are gases, you're going to have to use Kelvin. So I take my 41.2 minus my temperature, 298 times, and again, I switch this, I put a little mark here to remind you, I had to switch this from joules to kilojoules, so I just moved the decimal over 3. And so I get negative 0.97 kilojoules per mole, okay? And again, I put that little thing there so you can see I had to convert it from joules to kilojoules. So once you get your delta S, and when you look in the chart, they're in joules, so just move it over 3, okay? So this reaction is spontaneous because it has a minus entropy, or a minus Gibbs free energy, sorry. So we use this to determine whether a reaction happens or if it needs a little, kick in the butt to get going, okay? Here's another problem. We have carbon, here's another one, the same reaction, but now what we're going to do is we're going to change the temperature. We're going to raise the temperature. Before it was 298, I think, it was 298. Now it's going to be 700. So we're going to raise it quite a bit. So look what happens when we raise the temperature. We still have the delta H is the same and the delta S is the same, but now we're going to change the temperature from 298 to 700. And now we get 53.3 kilojoules per mole, okay? So now it's not spontaneous. The reaction is not spontaneous because we raise the temperature and we stop this reaction from occurring spontaneous. And you can do that. Like if you have, let's say, rusting, you don't want something to rust, you can do something, raise the temperature or something so that it doesn't happen. So we can use Gibbs free energy to calculate if a reaction happens, and then if we need to do something to change that, maybe we don't want it to happen or we do want it to happen, sometimes raising the temperature makes it more spontaneous. So again, it's something you can use to determine whether reactions will happen spontaneously or not. Okay, and here's a chart to kind of summarize it. Okay, so if your delta H is negative and your delta S is positive, your Gibbs is always going to be spontaneous. If delta H is positive and delta S is negative, okay, then it's never spontaneous. If they're both negative, it depends. If it's a low temperature, it's going to be spontaneous, okay? If they're both positive, it's going to be spontaneous at high temperatures. So really the thing that affects Gibbs the most is temperature, okay? But again, if you have a negative delta H and a positive delta S, it doesn't matter what the temperature is. It's always going to be spontaneous. Reverse it, positive and negative, it's never going to be spontaneous. So again, it doesn't matter what you do with the temperature. But if you've got two negatives, then you need low temp. If you got two positives, you need high temp, okay? So you can use this to find the boiling point because in that equation, the temperature that we use is can be used as the boiling point. If we want to find, if we have Gibbs free energy and the temperature, we want to find the boiling point, what we do is we set the Gibbs free energy to 0 because then it's in equilibrium, okay? So we're going to say 0 here. Delta H minus our boiling point, which again, this is our temperature, but if it's at equilibrium, this temperature is actually going to be its boiling point, delta S. So we take delta G and we set it at 0 because again, that's when it would be at equilibrium. That's when our temperature would be our boiling point. Okay, sorry, I have to put this on a couple slides. So to get the boiling point, let's say we have boron trichloride in a liquid to a gas state. And we want to figure out the temperatures. Now, looking on the chart, I have my H and I have my S. So I have to find my delta H and my delta S. Basically, remember, it's product minus reactant. So I'm going to take this number minus this one to find my H, and this number minus this one to find my S. Okay? So if I take minus 395 minus a minus 148, which would make it a positive, I get 23 kilojoules. So my delta H is positive. Okay? My delta S, again, I take this minus this, and I get 81. And again, I'm going to change it to kilojoules. So I'm going to move it over 3. So it's 0.081 kilojoules. So now I have my delta H and my delta S from my little chart here. Okay? So again, I plug in my formula. I set it at 0. So that's at equilibrium. 23 I found was my delta H. X, I don't know, that's my temperature. Okay, that's my boiling point. And then my delta S is 0.081, that's converting to kilojoules. So I get 23, move over to the side, 23 equals that minus 0.81 X. If I divide those two, it's going to equal X. So my temperature for this, my boiling point for this substance, occurs at 283.95. So anytime you want to find the boiling point of a substance, you can use the Gibbs thing by setting it to 0. That's when it's at equilibrium, and then just solve for X. Okay, so that's another thing you can do with the Gibbs free energy. And again, delta S and delta H are easy to figure out. You just look up the numbers in the chart. Okay, so if you're looking at a reaction, all reactions prefer to have low energy. They want a negative delta H. They prefer to have a positive delta S. This is the natural occurring things. This when reactions, this is what they prefer. So they want low energy and high disorder. It's kind of like teenagers if you think about it, you guys. They don't want to have to do a lot, but they want to be able to run around and do crazy if they have to, Now maybe that's not a good analogy, but you get my idea. Okay. The spontaneity of an reaction depends on these two factors, on the delta H and the delta S. And again, I showed you that on the chart. But there's some other things I want you to realize, okay? If you have a spontaneous process, it does not, it's going to happen without assistance. It's a normally occurring thing without any, you don't have to add outside assistance, the reaction is going to happen, okay? Processes that are spontaneous in one direction are non-spontaneous in the other. And you can look at my little chart here. We're going to drop eggs, and you can't see them, but they broke down here. Obviously, if you drop eggs, that's going to happen. So the spontaneous thing, if you drop eggs, is they're going to break, and you're going to get your yolks all over. Now, you can't put these guys back to that order. Maybe Humpty Dumpty, but they never did get Humpty Dumpty back together again. So you can't put the stuff back in the egg and put it back together, so it's non-spontaneous. So it happens this way, but it doesn't happen that way, okay? Now, one thing to remember, when I say spontaneous, that doesn't mean it happens fast. It could happen fast, but it doesn't mean it has to. There's fast reactions and there's slow reactions. So when we say spontaneous, it might take decades to happen, but it's going to happen without assistance. But again, don't confuse spontaneous with fast. Some are fast and some are slow. And again, don't confuse non-spontaneous with impossible. Okay? Now, this might be impossible, putting the eggs back together, but energy can be used to get reactions to go. You can change temperature sometimes. There's some things you can do to make a reaction that's non-spontaneous happen. Okay? So I wanted to clarify that, I guess. Some other things to remember: experimental factors that affect the spontaneous. Again, if it's not spontaneous, but you want it to be, temperature and pressure. Okay? If an example of how temperature affects spontaneity is ice freezing, melting or freezing, if you look here. Okay? If you go if the temperature is above 0, it's going to melt. So the spontaneous direction is that way. But if the temperature is below 0, the spontaneous reaction is this way. So you can change spontaneity by changing the temperature. Okay? And then I have this one, when we talk about reversible and irreversible, it might be a little hard to read. Sorry about that. But if it's reversible, the system changes, so the system and the surroundings can return to the original state. And there's many reactions that'll do that. Okay? So we can, in some, it maximizes work being done by the system on the surroundings. So this reaction, and again, it's a little tough to read, but if it's reversible, and again, you can tell if it's reversible if it's got the two arrows pointing both ways. The system will change, and again, it'll go back and it'll reverse the process. If it can't, if it's an irreversible reaction, okay, they cannot be undone. So the exact reversing doesn't change. So again, we had some of those reactions that weren't spontaneous, but we caused them to happen. Okay, but any spontaneous process is irreversible. Okay, you can still get the reaction to happen, but you're going to have to do something, and it's not going to go back. Here's an example in your car. You burn gas, and it causes little explosions, and it causes your piston to move. If it was reversible, then you wouldn't have to put gas in your car anymore. It would just keep happening and happening and happening. But we know that doesn't happen because we always get to put gas in our cars again and again and again and again, right? So anyway, this was just a couple diagrams I had to kind of explain it more. And then we are done with chapter 19.